time to start. Our next speaker is already ready, and we are happy to announce that now we know something new about new strong irregular graphs and a new partial geometry. So,
so can I start? Yeah, thank you. Thank you so much. First of all, I would like to thank the organizers for giving me an opportunity to be here and to present my work. My name is Andrea Švob, and I am with the Department of Mathematics, University of Rijeka. Today, I will talk about strongly regular graphs with parameters 81, 39, 12, and a new partial geometry. And I will try to explain you the recent work that is a joint work with Dejan Cinkovic and Vladimir Tončev. So I will try to explain you what we have done so far. There is a paper that we published recently on Archive, and I will mostly be regarding on the topic that is related with this work. Okay, so I have divided my talk into two parts. As the title said, I will speak about, in first part, I will speak about strongly regular graphs with these parameters. And then in the second part of the talk, I will show you how we constructed a new partial geometry. And in the second part, I will relate all my slides to partial geometry. Okay, so strongly regular graphs. It is well known that a strongly regular graph with parameters vk, lambda, mi, or shortly I will denote it as SRG vk lambda mu, sorry. It is an undirected graph with v vertices having no multiple edges or loops, such that every vertex has exactly k neighbors. Every two adjacent vertices have exactly lambda common neighbors, and every two non-adjacent vertices have exactly mi common neighbors. Okay, so in this work, we were interested only in strongly regular graphs, but not in strongly regular graphs in general. We were interested in a strongly regular graphs with parameters 81, 39, 12. Okay, so far, what we know about SRGs with these parameters. The first known example of SRG with these parameters was constructed in 1981 by Van Lint and Schrijver. And it is constructed by choosing a particular cyclotomic classes, and in such a way that it produced, or they constructed in that way, a strongly regular graph. Well, the work that they have been doing was relying on Del Sarte paper from '73, but all the description and more results which are related with Van Lint and Schrijver graph are also very nicely described in the paper of Calderbank and Cantor, the geometry of two-weight codes. Okay, why is that? This is because it is well known that any graph with parameters 81, 39, 12 that is invariant under the elementary abelian group of order 81, acting regularly on the set of vertices, can be obtained from a ternary linear two-weight code with parameters 15, 4, 9, and with a weight distribution words of weight 50 and 30. Okay, so after constructing Van Lint and Schrijver strongly regular graph, it is known that this strongly regular graph is connected with a two-weight code ternary with these parameters. So actually it means that when you obtain a two-weight code with these parameters, then it is two-weight, it has two weights, then you can construct a strongly regular graph in a way that adjacency is defined by choosing the proper words with particular weights. Okay, so it was known that one Lindenschreiber graph is constructed in this way regarding to projective two-weight code. In 1996, Hamada and Heleset wrote a very nice paper about characterization of some ternary codes and connecting these codes with mini-hypers. This paper is very crucial for for our work. Why? Because in this paper they showed that up to equivalence there are exactly two such codes that give rise to two non-isomorphic SRGs with parameters 81, 30, 12, and 9. One of each is gamma 1 that I will denote during the whole my talk, and it will be denoted for the one Lindenschreiber graph. And there is another one that is arising from the second such a code, and I will denote it to be gamma 2. In 2006, in the paper by Boyukliev, Fak, Willems, and Wine, they wrote a very nice paper about projective two-weight codes with small parameters. In this paper, these projective two-weight codes and these two non-isomorphic SRGs are very nice described, and you can find many other information regarding designs connected with these graphs, etc. So they describe it, of course, as the graph that are arising from two such codes. And it is known that they have a full automorphism group. One Lindenschreiber graph has 116640, and the second graph has a little bit, not little bit, but a smaller full automorphism group, which is of order 5832. Okay, so before we started to work on these SRGs, these two graphs appear to be the only previously known strongly regular graphs with parameters 81, 30, 9, and 12. Okay. In this work, we constructed more such graphs. When I say more such graphs, I mean the non-isomorphic, more non-isomorphic strongly regular graphs with parameters 81, 30, 9, and 12. And we used a different approach in a way that this approach is not connected with codes, neither two-way codes or codes. And these strongly regular graphs that we constructed are invariant under a subgroup of order 360 of the automorphism group of gamma 1. And there are exactly three such non-isomorphic graphs. And we constructed exactly 11 non-isomorphic SRGs, which are invariant under a subgroup of order 972 of the automorphism group of the graph gamma 2. So in the whole talk, gamma 1 is the strongly regular graph one Lindenschreiber, and gamma 2 is the second known strongly regular graph. The technique that we used here is based on the orbit matrices. Okay, so how did we construct it, and what was the construction that will lead us to new strongly regular graphs? Okay, so first of all, this construction is based on the two two methods. First of one is about. So in 2011, Bekbahani and Lam introduced a notion of orbit matrices of adjacency matrices of strongly regular graphs. And later, Cimkovic and Maksimovic, in their later work, generalized the construction written by Bekbahani and Lam. What was that about? So they introduced a method for constructing strongly regular graphs having a prescribed automorphism group. So they actually presume an action of some group that will be a possible automorphism group of a strongly regular graph. Okay, first of all, they constructed orbit matrices, and then they tried to obtain a strongly regular graph, actually adjacency matrix of a strongly regular graph from this orbit matrix. Okay, in the recent work in this paper, we generalize the notion of orbit matrices of adjacency matrices of strongly regular graph to an orbit matrices of Seidel and Laplacian matrices of strongly regular graphs. This was shown to be very useful in application for obtaining codes with very nice properties like self-orthogonal codes. So in this work, I will show you how we defined an orbit matrix of a general integer matrix. Okay, so let M be an n times n matrix. We need to define a permutation automorphism of a matrix M, which will be for us a pair of n times n permutation matrices P and Q, such that this relation holds. The set of all such pairs forms the permutation automorphism group of matrix M that we will denote by P automorphism of M. And an automorphism of a graph would be a permutation of the vertex set V that preserves the edge set E. Okay, so if we take a G to be a permutation automorphism group of an integer matrix M that acts in T orbits on the set of rows and the set of columns of the matrix M, we can denote the G orbits on rows and columns of the matrix by Ri and Ci respectively. And we can put that each orbit has the size capital omega I or omega I if we are watching G orbits on columns. And now we can denote Mij to be the submatrix of a matrix M that is consisting of the rows belonging to the row orbit Ri and the column belonging to Cj. And we will denote capital gamma ij and gamma ij, the sum of some row and some column of Mij respectively. And the sums of entries of any two rows or columns of Mij are equal. So the choice of choosing capital gamma ij and gamma ij is well defined. And the matrix that we obtain that has entries capital gamma ij will be called a row orbit matrix of a matrix M with respect to G, and with entries with gamma ij will be called the column orbit matrix of matrix M with respect to the group G. Okay, if we put that M is an adjacency matrix of a strongly regular graph, we are actually obtaining the orbit matrix that is defined in that is related with these two papers. Okay, so we have an orbit matrix of an adjacency matrix, we have a group that is acting in T orbits. Okay, so this is the first approach that I will need in order to explain you the construction. The second one is connected with the method that was introduced in 2014 in this paper. And it is described in this theorem. But what is it about? This theorem says that if you take a finite permutation group that is acting transitively on the sets omega 1 and omega 2 on two finite sets of size m and n, then you can take a particular, we can call it base block that is defined in this theorem. And if you act on this particular base block with the elements of the group G, you will construct one design with these parameters. This one design has the property that it is transitive, and it is transitive both on points and the group G acts transitively both on points and on blocks. We use this method for obtaining many transitive combinatorial structures, but particularly, for example, in this paper, this method was shown to be very fruitful because we applied that for constructing transitive, strongly regular graphs. And in this paper, we use it to actually prove the existence of a few particular strongly regular graphs for which parameters have not been known to exist before. Okay, but how we arrived to strongly regular graphs? It is actually corollary of this theorem, which says if you take that group G acts on the set omega, for which omega 1 and omega 2 in this theorem are equal, and if you take a base block, not arbitrary, but to be a union of self-paired and mutually paired orbits of a stabilizer of one element, then design would be symmetric self-dual design. But actually, the incidence matrix of that design is the adjacency matrix of a regular graph with regularity which is equal to the size of the base block delta 2. We say that orbit is self-paired if you take an orbit of a stabilizer G alpha, and if a group G acts transitively, then delta prime would consist of elements of this type. And this is also an orbit of the stabilizer G alpha. And we say that this orbit is called the orbit of a stabilizer that is paired with delta. And if delta prime is equal to delta, we say the delta is self-paired orbit. So actually, if you take a group G that acts transitively, if you take all self-paired or mutually paired orbits of the stabilizer G alpha, you can obtain a regular graph. Of course, that each regular graph does not have to be a strongly regular. For obtaining strongly regular graph, then you have to include some other conditions in which from all these regular graph, you will take just those that are strongly regular. This corollary and this theorem actually tells you that using this construction, you can obtain all structures on which the group G acts transitively. And this fact was actually very, very important for the construction that we applied in this research. Okay, so in one construction described here, you have a transitive action of the group G. In defining an orbit matrix, we have that the group G acts in few orbits so it does not have to be transitive. But what did we do? We take the group G that does not act transitively. It acts in some finite number of orbits on the set of vertices in this case, but it can be also a set of points. And we observe each orbit as in a way that we apply a transitive action just on that orbit. Actually, we split non-transitive action into few transitive actions in which each of these transitive action we applied the method for obtaining transitive combinatorial structures. I will show you now in concrete what we have done. So remember that we know already gamma 1 and gamma 2 in their full automorphism groups G1 and G2 of orders 116640 and 5832. Okay, so new SRGs are constructed by presuming an action of subgroups of G1 or G2. Now I will present you the subgroups that we used for obtaining new strongly regular graphs. It does not mean that we did not try to construct new strongly regular graphs from other subgroups. We did, but I will here just describe you those that leads us to new strongly regular graphs. I have to remark here also that computationally this was not very easy. The method is can be explained in these few slides, but applying this in the computer program in which you have to check for subgroups and try to reach all subgroups if you can was a very demanding process. Okay, so let's start with first part of results. So in this first part, I will explain you SRGs that are admitting an action of a subgroup of automorphism group of gamma 1. So we know that there are exactly 4 conjugacy classes of subgroups of order 360 in the full automorphism group of G1. In total, G1 has more than 1050 subgroups, of course, up to conjugacy. And this is one conjugacy classes, 4 conjugacy classes of subgroups of order 316. The representatives of each of these 4 conjugacy classes I will denote with H1 and H4, where 1 is always here, and it is regarding the strongly regular graph gamma 1. Each of these representatives is isomorphic to the simple group A6. Okay, so the group H1, what we know that it acts in 2 orbits on the set of vertices of the graph gamma 1. So it acts in 2 orbits on the set of 81 elements. One orbit is of size 36 and the other is of size 45, and it leads to an orbit matrix of order 2. So we know that this is an orbit matrix for an action of the group H1 on 81 vertices of the graph gamma 1. And these are the elements of an orbit matrix. Okay, so for sure we know that this orbit matrix has to produce a strongly regular graph from which we started, which is a Van Linde and Schreiber graph. But the same orbit matrix can produce many other strongly regular graphs that have the same parameters as Van Linde Schreiber, but does not have to be isomorphic to those, because two strongly regular graphs can have for the action of the group G the same orbit matrix, but they not have to be isomorphic. Okay, with this orbit matrix, so it is of order 2, so it means actually then that on each of the element of this matrix we applied our transitive action. So we actually in some way enlarge this orbit matrix in a way to produce an adjacency matrix of adjacency matrices of possible strongly regular graphs. From this orbit matrix and the group 360, which is actually H1, we obtained two non-isomorphic strongly regular graphs, gamma 1 that we needed to obtain, and I will denote it gamma 14. You will see in the table later where I summarize the results. That has the full automorphism group of order 360. And this was the first one that was new because he was not isomorphic to known before. H2, we repeat the process on H2. It acts in 3 orbits. So orbit matrix is of order 2. And it produces us 2 non-isomorphic strongly irregular graphs, gamma 1, Van Lindenschreiber, and gamma 13, which has the full automorphism group of order 720. Okay, I forgot to say that this full automorphism group is isomorphic to A6, and this is symmetric S6 group. H3 produced one strongly regular graph isomorphic to gamma 1, and gamma 4 also produced one strongly regular graph which already known before gamma 1, and this is obtained from this orbit matrix of order 4. So actually, starting from automorphism group of Van Lindenschreiber, we obtained 2 new non-isomorphic strongly regular graphs with the same parameters as Van Lindenschreiber. The similar process we obtained for SRGs admitting an action of a subgroup of automorphism group of gamma 2. There are exactly 5 conjugacy classes of subgroups of order 972 in the full group automorphism of the G2, which is of order 5832, and representatives of which I will call H1 to H5. H1 and H2 act transitively on 81 vertices, and they produce 2 non-isomorphic strongly regular graphs, gamma 1 and gamma 2, of orders that are those of orders of automorphism groups of gamma 1 and gamma 2. Action is transitive. This full automorphism, these groups contain elementary abelian group acting regularly. So actually, we had to obtain, which is okay. H3 is acting very nice on the set of 81 vertices, and it acts in 3 orbits of length 27, and with this orbit matrix. So from this orbit matrix, we obtained 2 non-isomorphic strongly regular graphs, again gamma 2 that we started from, and a new graph, gamma 4, with the full automorphism group of order 1944. H4 and H5 are acting in the same way. What does it mean? It means that they are acting with the same orbit matrix with 2 orbits. So the orbit matrix is of size 2. The orbits are sizes 27 and 54. Okay, from H4 we obtain 4 non-isomorphic strongly regular graphs, and from H5 we obtained 12 non-isomorphic strongly regular graphs. 8 of these strongly regular graphs have a full automorphism group of size 972, and one has this full automorphism group. So we can see actually that this other graph that has a smaller full automorphism group produces us much more non-isomorphic strongly regular graphs. In this table, I summarize the results that we obtained so far. Okay, so in the first column, the first and the second column, you can see the strongly regular graphs with its full automorphism groups. So from 1 to 4, you already see that they are definitely non-isomorphic. They have different full automorphism groups, and gamma 13 and gamma 14 also. Gamma 5 to gamma 12 have the same full automorphism group. So we started to play a little bit more with those that have the full automorphism group to try to distinguish them as much as we can. First of all, we calculated the 3 rank of the adjacency matrices of these strongly regular graphs. And here is the information for this. And we constructed ternary codes from these adjacency matrices, and we obtain this set of parameters. And these codes are very interesting because they are self-orthogonal. Okay, then we ask what is the click number of these strongly regular graphs. Actually, what is a size of maximum click of graph gamma. Remember that gamma 1 and gamma 2 have been already known, and all of the rest have click number 6. We counted how many 6 clicks we have, and we obtained this number. Then we moved forward with these 2 columns. What I will come a little bit later again, because they were interested for us for defining partial geometry. But here they are very useful because with them we can distinguish also some of these non-isomorphic strongly regular graphs. So we defined gamma star new graph to be a graph. How we defined this graph? We took the set of all 6 clicks in started gamma graph, in the starting gamma graph, and we took vertex set of gamma star to be the set of all 6 clicks. And we were interested just in those that have more than 81 6 clicks. So this is the set of vertices, and the adjacency is defined that 2 vertices are adjacent if intersection of corresponding 6 clicks is of size at most 1. So we obtained this new graph, gamma star. In the last column, we counted the number of 81 clicks, but more about that in the slides that I will show you. Okay, but what we know so far, we can see from these few columns that we cannot distinguish gamma 5, 7, and 8, 6 and 11, and 9 and 10. So we have to try to find more properties that can help us to distinguish these graphs. We defined an incidence structure for each gamma I in a way that we've taken that the points of that incidence structures are the vertices of gamma I, and the blocks are all 6 clicks. And we construct these incidence structures for each of the graph gamma I to gamma 14. We calculated the size of automorphism group of this incidence structure and the length of orbits on points and on lines. And with this information, actually, we could distinguish those graphs that that we had to distinguish. Why? Because now we can see that gamma 9 and 10 cannot be isomorphic, because the corresponding incidence structures have different automorphism groups. The same goes from gamma 6 and gamma 11. And for gamma 5 is different than 7 and 8. But we still have to distinguish gamma 7 and gamma 8. So we took the weight distribution of the ternary code that is spanned by the adjacency matrices of the graph gamma 7 and gamma 8. And we saw that the smallest weight in which they are different is 33. Of course, they are different in the bigger weights, but the smaller one in which we can distinguish them is 33. So actually, we were now happy with this description in which we could distinguish all the obtained graphs. Moreover, I have to remark here that we also established that there are exactly two SRGs with parameters 81, 39, 12, admitting the regular action of the elementary abelian group 81, which are the previously known SRGs. So we actually confirmed the result that there are exactly two inequivalent ternary two-weight codes with these parameters. Okay, but someone can ask a very logical question, but why did you, in the start, were interested in strongly regular graphs with these particular parameters? So actually, we were interested in these graphs because of a partial geometry. Okay, so but let's go firstly to a few definitions. The definition of partial geometry that says that the partial geometry with parameters st alpha, or shortly I will denote it PG st alpha, is a pair that consists of a set of points and a set of lines with the incidence relation between points and lines that is satisfying the four axioms. A pair of distinct points is not incident with more than one line. Every line is incident with s+1 points, and every point is incident with exactly t+1 lines. And the last one, that for every point that is not incident with exact line, there are exactly alpha lines which are incident with p, and also incident with some point that is on line L. They were introduced by Bose in '63. But in original paper of Bose, he was using the little bit different terms. He was using V and big K for our letters ST and alpha, but I will here regard as ST and alpha. So it is known that in terms of ST and alpha, we have equation 1. So we can count the number of points and the number of lines of partial geometry. It is also known that if we switch partial geometry in a way that we define an incidence structure G prime having as points the lines as points, an incidence relation that point and line are incidents in G prime if and only if the corresponding line and the point are incident. We defined a dual partial geometry. Partial geometries are connected to strongly regular graphs. So the point graph of a partial geometry is strongly regular. We can define a point graph to be a graph whose point set is a point set, whose vertices are the point set of the partial geometry, and the lines L. So we can define adjacency that two vertices are adjacent if the corresponding points are collinear. The line graph is the graph having as vertices the lines, where two lines are adjacent if they share a point. And it is well known that point graph and line graph of partial geometry are strongly regular graphs, and parameters of these strongly regular graphs are given by equation 2. Examples of partial geometry, when you have that alpha is s plus 1 is a Steiner design. Dually, of course, when alpha is t plus 1, you have a Steiner 2 design with these parameters. If alpha is s or alpha is t, then you have a net. And if alpha is 1, you have a generalized quadrangle. We will be talking about proper partial geometry for which alpha is between 1 and a minimum from S of t. And what is most important is the fact that a strongly regular graph whose parameters can be written as in form of the equation, in equation 2, is called pseudo-geometric. So if you have a parameters of a strongly regular graphs that are satisfying the equation given by Bose, then this graph is called pseudo-geometric. But if you can moreover construct a partial geometry, or if there exists a partial geometry with parameters st alpha such that gamma is the point graph, then you will call this graph geometric. Bose gave a very, very nice theorem from '63 that helps you to check whether your strongly regular graph is pseudo-geometric or it is geometric. So it says that if you have a strongly regular graph that is satisfying the parameters in order to that this SRG is pseudo-geometric, it is geometric if and only if there exists a set of V clicks in this strongly regular graph of particular size S plus 1, such that every 2 clicks from S share at most one vertex. And this is actually the way how you can check whether your strongly regular graph is geometric. Finally, we arrived for the result. So the known proper partial geometries can be divided into 8 types. 4 types are infinite families, and there are 4 sporadic geometries that are not belonging to any known infinite family. You can see more in handbook, but we were particularly interested in one such sporadic example, which is a partial geometry with parameters PG552, which is discovered by Van Lint and Schrijver in 81. So when they constructed strongly regular graph with parameters 81, 39, and 12, actually, they constructed also a partial geometry with these parameters. We already said everything for Van Lint graph. It is now, we will denote it as a point graph of a partial geometry with parameters 5, 5, 2. This partial geometry has a full automorphism group of order 58,320. It is actually the size of automorphism group of a strongly regular graph of Van Lint divided with 2. And this was the only known partial geometry with these parameters. We constructed in this work 12 new strongly regular graphs with parameters 81, 39, and 12. And one of these new graphs is geometric. This was a very, very nice graph that was geometric because it produces a partial geometry with parameters 552, which is not isomorphic to the partial geometry discovered by Van Lint and Schrijver in 1981. That's why these two columns were very important for us, how we check that our graphs are that our graph is gamma 12 is geometric. So after constructing gamma star, we checked how many 81 clicks it has. This one has exactly 181 clicks that is giving us a partial geometry. Though that partial geometry known before has two sets of 81 clicks, but it produces an isomorphic PG. This, our graph, geometric graph has 108 6 clicks. 81 of them form the lines of the new PG. And this new PG has the full automorphism group of order 972. And this full automorphism group acts very nicely. It acts on the points and the blocks of the PG in two orbits of lengths 27 and 54. What else we can say? We can say, and we check, it is a self-dual. Its line graph is isomorphic to its point graph. Here, I have to remark that after we constructed our new partial geometry graphs and we saw that simultaneously and independently on arXiv, it appeared a paper by Vedran Krčedinac in which he constructed the partial geometry that is isomorphic to our partial geometry with parameters 552, but the method that he used is another method, and it is not connected with our method. He based his method on geometrical structures. So in this paper, actually, we proved that up to isomorphism, we constructed 12 new non-isomorphic strongly regular graphs with parameters that are invariant under these subgroups. With this known 2, that gives us at least 14 mutually non-isomorphic strongly regular graphs. But one of these new strongly regular graphs yields a partial geometry which is not isomorphic to the one constructed by Van Lint and Schrijver. Okay, and with this slide, I will conclude my talk. Thank you very much for your attention.
Thank you very much for such a perfect explanation of the results obtained. Thank you. So, are there any questions to our speaker?
Can I ask a question?
Yeah, sure, please.
Okay, thanks for the talk, Andrea. Very nice. In the original paper by Van Lint and Schrijver, they also construct association schemes. And in particular, there's also the construction of the Brouwer-Hamers graph in there. So in your constructions, did you try to find also the Brouwer-Hamers graph in connection to these?
No, this is a very, very recent work. We finished with this graph, and this is something that something that we will try to do.
Yeah, because if you find the Brouwer-Hamers graph in the complement, then what remains is also a graph of your type. So you could find even more graphs.
Mm-hmm.
Yeah. Yeah. We stopped here because when we found this new partial geometry, and when we put it on archive and saw that somebody else also constructed, we were afraid and said, okay, now it's time to stop. Let's focus on some other things. So it was, but yeah, definitely here we have many other things that we are working on now. Yeah.
Thank you.
Yeah, thank you. Yeah, any other questions, please?
If I may.
Oh yeah, sure, please, yeah.
You said when this this first family of graphs, you said these groups were isomorphic to A6 and the symmetric group of order 6.
Yes.
But this group of order 972, does it also have a nice description?
970, no, it does not have. Well, it is a direct product of some cyclic group. It does not have nice description.
Mm.
The one of order 360 has, it is A6 and the 72 is S6, but this one doesn't have nice description. That's why we didn't describe it in that way.
Okay, thank you.
Mm-hmm. Okay, are there any other questions? Okay, I just would like to know, you mentioned about some other approach to get the same geometry, right? Yeah, so the new partial geometry. And are there any relationships to strongly regular graph at that approach?
In that approach,
yeah.
No, I think
no.
That the author, he was interested just in the partial geometry, and he somehow, I didn't went detailed in this paper, he was using some geometrical properties of some particular sets, and he constructed PG 552. So he did not start from SRGs, he was not interested in SRGs. He went directly in geometry.
I see. And another question is about computational results. You mentioned in your talk that it was too complicated.
It was very
well,
yes.
Yeah, I don't understand, but which software did you use?
Well, few of them. The main was Magma, and in Magma we've done all the computations with groups, with graphs, while constructing orbit matrices. This was very demanding, constructing adjacency matrix for an orbit matrix, because when you are dealing with a group, we had to be very careful about each function, each stabilizer. This was not very easy to put in the program. Okay, but we managed that. So we've done that everything in Magma. And then for checking and trying to find clicks, we used Sage and Clicker. So because in Magma, we couldn't compute nothing with clicks. So we had to go on the other softwares that were more fast on this type of problem.
But you didn't mention GAP, because it seems to me that one can use GAP as well.
Yeah.
For the second part, I mean.
Yes,
right?
We can use a GAP also in the same manner as we used Magma. But since I am used to use Magma, then I don't know. It can be do in GAP also. But concrete in this work, we were not relying on GAP.
Okay, I see. Okay, thank you very much. Yeah, thank you. Are there any other questions, comments, suggestions to find new geometries or graphs? Okay. No. Andrea, well, it was really very nice talk. Thank you very much. You explained all details with a very nice background and new methods. So thank you very much. Yeah, I impressed a lot. Thank you.